Hey, good afternoon. My name is Brian Yandel, and I'm a professor of statistics, one of the three departments in the School of CDIS. And I'm also the founding director of the American Family Insurance Data Science Institute. The Institute was formed in 2019 with the three-part mission to innovate, translate, and collaborate across where data science intersects other fields. And I'd like to introduce Kyle Cranmer, who is currently the executive director of the Moore Sloan Data Science Environments and professor of physics at New York University. And he will be coming here in July, but he's here virtually with us right now. He was also instrumental in forming the Academic Data Science Alliance, or ADSA, and UW-Madison is one of the founding members of this alliance with DSI as the founding institute and CDIS as a collaborating partner. Now, without further ado, I'll turn it over to Kyle.
Okay, great. Thank you very much, Brian. Let me share my screen. Great. Can you see that? Look fine? Okay, great. Okay, well, thank you very much for having me. It's really an honor. I'm looking forward to coming back to Madison. So the title of my talk today is Data Science is on its feet. Now, where is it going? So I wanted to start actually by saying thank you to Brian, who's been very gracious with his time and helpful in trying to get me up to speed and on board as I take on this new role in July. I also wanted to thank right away American Family for their very generous gift. They've agreed to invest $20 million in the University of Wisconsin's Data Science Initiative, including $10 million to start the Data Science Institute itself, and another $10 million over the next 10 years to support research in the form of seed funding. And thus far, there's already been $3 million of support to over 21 different teams. So that's a very big boon to data science in Wisconsin, and so thank you. I would also like to highlight the Data Science Institute staff, both the kind of management and communication side, the facilitators that are doing a great job of running various kinds of events and training and et cetera around campus, and then staff that's in terms of data scientists and software engineers who I've getting to know and starting to work with, and I'm really looking forward to seeing you all in person. Also, I am pretty excited about the new building that CDIS is going to have. The Data Science Institute will be housed in CDIS once it's ready, and so that, I think that will be a very thriving and exciting place to be, and I'm looking forward to all of that. So I'm going to start this this journey with a kind of historical background about sort of the origin story for data science. So that we can better appreciate how it got on its feet and think about where it's going and to what degree what that evolution looks like. So to do that, I'm going to start off with going back to antiquity with this timeline of statistics prepared from the Royal Statistics Society, and zoom in to around the millennium, and in particular point out that around 1997 or so is the first time big data was seen in print. And at this point in time, big data was really kind of the buzzword of the time. The internet had just sort of taken off. There was a tremendous amount of data being generated, and everything was changing very rapidly. And as I came into grad school, big data was a sort of rising theme. So this is sort of from a personal point of view, the timeline. In 2000 is when I first arrived in Madison to start my PhD. I graduated around 2005. I was working in physics, preparing for the Large Hadron Collider at CERN. I started as a professor at NYU around 2007, and the LHC began basically the next year. And with this in mind, the idea of big data and the data deluge was very familiar to me, because the Large Hadron Collider was not only like physically the largest experiment that humans had ever made, it was also about to produce the largest data set in the history of science. producing something like 700 megabytes of data every second, which is something like 15 petabytes per year, which at the time was really, I think, far and away the largest data set that anyone was sort of dealing with, at least in science. So this was an article published in 2008, right as the beginning, as the LHC was turning on. I'd also like to sort of give a shout out to Marone Livni, who I actually knew as a graduate student. He did, with his Center for High Throughput Computing, he did a lot of very, very important work in establishing the infrastructure that was needed to be able to produce, to process that much data. We as a field sort of owe a lot to what Marone has done. And I'm excited that I'm, still getting to work with him and collaborate with him, and I'll see him more soon. But at the same time, as the LHC was turning on, you also saw in the media these kinds of articles that were coming out, which were very different than how I thought about big data as a physicist at the time. And so you see, the idea that big data is somehow spelling the end of theory, and that the data deluge is going to make the scientific method obsolete. And of course, there's some journalistic hyperbole here. But this was a serious discussion, and I think lots of people were kind of going down this mental route. And if you look in these articles and around the time, you find quotes like this from Peter Norvig, who at Google, who says all models are wrong, and increasingly you can succeed without them. And so this, if you're not familiar, is a play on words from a famous quote from the statistician George Box, who quipped that all models are wrong, but some are useful. And I think it's worth understanding a little bit what is this tit for tat that they're having here. And I think one way of understanding that is to discuss briefly this paper by Leo Bremen that came out in 2001 about statistical modeling and the sort of two cultures of statistical modeling. And I'm going to read from the abstract here. It says there are two cultures in the use of statistical modeling to reach conclusions from data. One assumes that the data are generated by a given stochastic data model. That just means like some probabilistic model for the data, like a traditional statistician would talk about. The other uses algorithmic models that treats the data mechanism as unknown. And the statistics community has been committed almost exclusively to the use of data models. That's what he calls them. And this commitment has led to irrelevant theory, questionable conclusions, and has kept statisticians from working on a large range of interesting and current problems. So it's pretty strong words. In contrast, he talks about algorithmic modeling, both in theory and in practice, has developed rapidly in fields outside of statistics. And it can be used both on large complex data sets and also more accurate and informative alternative to data modeling on smaller data sets. So sounds pretty good. And he says, and if our goal as a field is to use data to solve problems, then we need to move away from exclusive dependence on data models and adopt a more diverse set of tools. So you both have some pretty strong language and some pretty critical things, and also at the end, a very reasonable statement, which is just talking about growing our tool set, and it's hard to disagree with that, the last point. And in fact, I'd just like to say that in an earlier CDIS Red Talk, Mark Shar was talking about design thinking, and I like this slide that he showed, which says that problems are different, and it's important to match the problem solving style to the problem and the tools in your toolkit. And so I think that adding more tools to your toolkit certainly doesn't hurt, and we don't have to make it some sort of binary choice or something like that. Now, in Bremen's paper, he talks about sort of, on the left, he's imagining, real, whatever's actually nature is doing to produce data. He's really couching everything in terms of a kind of curve fitting, dependent, independent variable setting, where on the x-axis you have something like knob you can control, and the y-axis is some sort of a response, and nature is playing the role of that response curve. And he's talking about in classical statistical modeling, the way that you would go about doing this is, try to describe that process. And he, talks about the papers that you would typically read in statistics would always sort of start with a sentence like, assume that the data are generated by the following model, ... right? In contrast, what he was talking about, which I think now we would just call machine learning, or more specifically supervised machine learning, was not going to make the same kinds of assumptions. And instead, you're going to work with a much richer class of models. You might refer to it as even model-free. They're kind of black box. They don't have some sort of story or simple equation, to describe them. And then the way that you will kind of assess the model is through predictive accuracy or what's sometimes called cross-validation. So in this paper, he goes on, when he's criticizing the kind of traditional statistical practice, he says the enterprise at the heart of it has the belief that statisticians, by imagination and by looking at the data, can invent a reasonably good parametric class of models for a complex data mechanism devised by nature. And then he goes on to say that once you fit the model, the conclusions you make are really about the model's mechanism, not about nature's mechanism. And if the model is wrong, then your conclusions may be wrong as well. And so, I think that these are all sort of reasonable statements, but he sort of takes that into a very kind of opposite, extreme. Which is which is basically machine learning and its early forms, as we saw it, talks about neural networks and decision trees, talks about complex prediction problems, and importantly, the fact that these kinds of models were able to deal with very complicated, rich data like you would find in speech recognition or image recognition, financial markets, things like that. And so this, I think, is a lot of the background that is driving these kinds of quotes that you see in a lot of the thinking around big data. And I guess just this point again is that the criterion for the model is basically how good is it at predicting things. So if you take data that you haven't seen before and you stick in an X and it predicts a Y, how close is that to what nature actually did? So like I said, I think this is what Peter Norvig is sort of getting at when he talks about increasingly you can succeed without them. And this was a lot of the thinking and excitement around, big data and what you could do with it. And I'd say that peak big data happened somewhere roughly around 2011 with this McKinsey report, which was actually very important and influential because it pointed out the sort of financial and business opportunities, the need for talent, the shortage of people that had this kind of expertise and the job opportunities, and that then influenced a lot. So it was a very important report that came out. So also around this time, a little bit earlier, there were articles that started coming out where you start seeing data science as a term being used. And it's often, and at least its current use, not necessarily the first time that the words were ever used together, but in its current use is largely attributed to DJ Patil and Jeff Hammerbacher. DJ Patil was the chief scientist at LinkedIn. Jeff Hammerbacher set up the sort of data team at Facebook in the early days. And they got together and were talking about their data analytics crew and what was different and what was going on. And this meeting, it basically was the start from their point of view of thinking about data science as a distinct professional specialization. I had the pleasure of talking to Jeff about some of the stuff in the past. So, and I also think it's important to talk about this part of that article where he says about being data driven. And there's sort of this assumption that everyone wants to build a data-driven organization. And it does sound good. And, we're talking about the Center for Data Science and the Data Science Institute and CDIS and et cetera. So data is certainly important. And he does go on to say what he means by that. And he says a data-driven organization acquires, processes, leverages data in a timely fashion, creates efficiencies, iterates and develops new products, and navigates the competitive landscape. So it's very much a business industry point of view, which makes sense given that he's coming from LinkedIn. And there were some other articles around that time, but it's definitely that first use of data science was really data science in this kind of professional setting, this kind of industrial setting. The other thing that popped out around that time that was kind of influential in the early, discussions around data science was this Venn diagram from Drew Conway. Apologies if you're tired of seeing this and you already know it, but he's basically putting together a few different things. So he's talking about, if you think about, kind of standard mathematics and statistics knowledge and substantive expertise like you would have, say, as a physicist or a chemist or something, that intersection is kind of traditional research. And as you pair it more and more with kind of computing and what he called hacking skills, because sometimes it's a little bit more fast and loose about cobbling things together to kind of get the job done, that's where you start to see something that looks more like what he thought of as data science. And if you remove the domain of application from that story, then you're kind of left with machine learning. And so data science kind of at its core had a domain of application as an essential ingredient. And then he also points out that if you try to do this hacking and you're, say, a physicist, but you don't know your statistics, then you can get yourself into trouble, and that's the danger zone. Okay, so again, around 2011, and I will be kind of done with a lot of the historical stuff pretty soon, Jan LeCun at NYU wrote this manifesto, basically calling on the university to invest in creating a Center for Data Science. If you read through that manifesto, there's a lot of emphasis on the themes that I was just discussing, and a lot of references to those specific articles and things that I showed you. So there's an emphasis on big data, being data-driven, automation, productivity, efficiency, competition, and a lot of themes that are very important in the kind of industrial setting. The skills that are being focused on are statistics and computer science and information science and applied mathematics. There is some attention, but I'd say only moderate attention to the knowledge and expertise that of a certain domain of application. And there's really little attention paid to the importance of understanding. And I'll come back to that towards the end. And also missing, kind of notably from the discussion at this point, are the potential adverse impacts of all of this on society. So this was 2011. So in our timeline of statistics, we had the kind of introduction of data science over the next decade. Big data over the next decade. The discussion around big data turns into kind of data science. Interestingly, shortly after that is the discovery of the Higgs boson. So during a lot of this time, my focus was largely in particle physics. We were certainly dealing with big data and computing and statistics and all of these things, but it was really in a particular context. Now, another very important thing happened in July 2012. So on one side, we announced the discovery of the Higgs particle, which was very exciting for me personally, and a really important achievement for humanity, I'd say. But the other big thing that happened was this sort of breakthrough in deep learning. So it's surprising, it was really the same month, July 2012, that this first kind of breakthrough paper in deep learning happened. And it was an image classification task. It was using deep neural networks, where the basic idea was the kinds of ideas that people had had for decades that it just never got it to work. And the reason it started to work was there was more data to train it. That was the ImageNet data set had 1.2 million high resolution images. There were advances in computing, particularly GPUs. Also, the software kind of toolkit for doing these optimizations improved. And then there were some tricks that were in terms of how to train these models and get them to work well in terms of what you would call regularization, in particular something called dropout. So at this point, deep learning starts to work. It captures the attention of the world. And we are really seeing now a huge shift of the pendulum swinging from kind of traditional modeling approaches with handcrafted data analysis, largely guided by expert knowledge and theoretical insights, way over to the other extreme of sort of big data and deep learning that eschews expert knowledge, embraces end-to-end learning, and it really focuses on being data-driven almost obsessively. And so deep learning, when it came out, it really, this is kind of zooming ahead in the future, but it really took off, right? So these are the number of papers submitted to the kind of big machine learning conference called NeurIPS from 2014 to 2019, and you see almost exponential growth, growing to 6,000 papers, almost 7,000 papers submitted to one conference in a year. This is the number of attendees growing from less than 1,000 to more than 8,000. In 2016, I had the surreal experience of being invited to give a keynote at NeurIPS, and this is what the crowd looked like. I was like speaking to a sea of people, and it only got bigger from there. So while I am very excited and very interested in machine learning and AI, a lot of the narrative of this talk is actually, somewhat critical, but also pointing out opportunities that I think are very, very exciting and how that kind of fits into data science. Okay, so here we are in our timeline. We had the rise of deep learning starting around 2012. We had the first academic data science centers and institutes being created basically in 2013, the next year. And so I want to talk now a little bit about the birth of data science in academia. So probably, from my point of view, one of the most influential things that happened here was that the Moore and Sloan Foundations made a really major investment. The Moore Foundation put almost $80 million into a data-driven discovery program that they had, which included this partnership with the Sloan Foundation to create the Moore Sloan data science environments. That picked 3 universities, Berkeley, NYU, and the University of Washington, and they gave $12.5 million to each institute. And a lot of the focus here was really, what can we do to drive institutional change to try to make it so that academia is a good place to do this kind of research, and there wouldn't be a huge brain drain, and that the impact of all of these developments on science would be missed. And so they wanted to make sure that academia was ready to kind of embrace this and leverage these developments. I will note that the phrasing that was used at this time still really puts a lot of emphasis on data-driven, and it makes sense if we're talking about a data science. Data-driven seems like a very natural term, but I'll try to kind of make the point that there is a little bit of tension between this sort of data-driven end-to-end picture and something that's more traditional, where you have like domain expertise and something more like traditional scientific models. And it's also a little bit ironic, because once we actually set up the Moore Sloan data science environment, these 3 universities were collaborating very closely. The way that we organized it, and the way it was really organized from the beginning, was not like all AI and machine learning or something. It was really, on one side you had data science methodologies, on the other side you had domains. It really embraced the idea that data science only makes sense kind of when couched in a particular, in a certain domain, in a certain context. And it emphasized a lot this virtuous cycle where new data science methodologies would transform discovery, and then advances from the scientific areas would then spur new data science methodologies. So this kind of virtuous cycle was really built into the culture of the 3 institutes, and I think has survived largely, if not entirely, into the kind of evolution of data science across academia in the United States. Now, I'll also say that around the same time in 2014, the National Science Foundation started to really emphasize what they called use-inspired research. And there's this article that I point to here where the National Science Foundation is trying to explain this. And what they are trying to explain is that on one side, you have kind of purely applied research where you're trying to solve a given problem and you just want a tool that will get the job done. And then you have pure foundational research, or pure basic research up here in this quadrant. And they're trying to distinguish between those and establish another quadrant here, which sometimes is referred to as Pasteur's quadrant, which is what they call use-inspired research. And the claim here is that many foundational advances that we see are often inspired by the context and the peculiarities of a specific application problem setting. The way I think of it is sort of reality is stranger than fiction. You wouldn't think to explore certain kinds of opportunities until you really see that actually is a constraint that's being imposed upon you by whatever the application setting happens to be. Another way of thinking of this is that necessity is the mother of invention. So the idea here is to really have a kind of deliberate activity that tries to abstract from the pure applied research and try to pull out what's novel, what's new, what's difficult here to drive foundational advances. So with that in mind, we can now think of data science sort of in different kinds of contexts. So the way we started was really industry as context, and there's clear value and need for data science, and I'm absolutely on board with that role of data science. It really dominated the initial framing of the phrase. And then what we saw kind of after that was a wave where okay, well, if you are going to automate all of this stuff, that's going to have consequences. And then we started to see sort of societal concerns as context, right? So what is the impact of automated decision-making systems on society and marginalized groups? And then you start seeing different kinds of themes coming to the fore, like privacy and ethics, explainable, audible, transparent, responsible, trustworthy AI and data science techniques. And this is really, a very active area, and it's there's some, I wouldn't say exactly tension, but there's there are competing interests here in terms of these two different sets of concerns. And industry has certainly taken note, and industries that are successful take this to heart and really try to integrate it from the ground in their data science practice. The other context that I'll speak a little bit about is science's context. Again, I think here there are really clear opportunities. You obviously have a data deluge here as well across the sciences, certainly like physics and astronomy, also like genomics, multiomics, health sciences, et cetera, there's data all over the place. But in the scientific context, there's, I would say, increased emphasis on understanding and interpretability, which we didn't necessarily see as like the emphasis on in the industrial context. So one analogy that I like to use for data science and trying to think about like what is data science is a globe, and to think of data science not really as a specific domain, but as kind of a direction. If you contextualize data science in a particular domain, like say chemistry or health or social science or political science, the way that you take that domain and sort of move it in a more data science-y direction is similar to being at different points on the globe and thinking about which way is north, right? In an absolute sense, they kind of point in different directions, but they're all sort of heading to the same goal. At the same point in time, if you went all the way to the North Pole, you've kind of at that point, you don't distinguish between the different domains anymore. And that's kind of like the pure methodological aspect of data science, which then doesn't necessarily have the kind of domain of application anymore. Okay, so now let me spend a little bit of time talking about the sort of scientific context. This is certainly where I was coming from when I first got into it. I'm going to talk about use-inspired research. Just give a couple quick examples of famous cases of foundational advances in data science and statistics that were inspired by physics. So one of them, for this maybe more for the experts, but in Bayesian statistics, Markov chain Monte Carlo, or MCMC, is like really a workhorse there that does all sorts of things and really transformed computational statistics. And that was originally motivated actually from thinking about calculations people needed to do in the context of nuclear weapons at Los Alamos in the 1940s. And Ariana Rosenbluth, shown on the top right, was the first person to actually implement the Metropolis-Hastings algorithm, which I think is pretty cool. More advanced forms of these kinds of ideas, for instance, Hamiltonian Monte Carlo, were also motivated and first proposed in the context of theoretical nuclear physics. And many more approaches have been developed in the context of molecular dynamics, quantum systems, et cetera, et cetera. And these, they were motivated by that, but they've had impact all across the board in terms of data science. Another, important technique that we see in statistics is called variational inference. I'm not going to get into what that is or how it works. It also has its origin in physics, in particular in the context of statistical mechanics and things like free energy and thermodynamics and stuff like that. And here are some pictures from a talk that David Bly gave, where variational inference, interestingly, is, it combines both a generative model for the data like a kind of classical statistician would use, and also scales to big data. So here you see things, 3.7 million nodes in a network, 220 million functional MRI measurements, et cetera, 1.7 million taxi trajectories. So these are all very data science-y applications. It's using a statistical technique that both can scale, take advantage of all of the computational things that are going on, but does not dismiss the idea that there is a interpretable model at the background that is sort of generating the data, which I think is really, really important and influential. So going in this direction, there's a new development, which is where a lot of my research is in, which is to say that if you really want to go to the extreme of modeling, data modeling that scientists do, that's where I usually think about simulators. So in particle physics, we have simulators that are very high fidelity that describe what the collisions at the Large Hadron Collider look like. My friends in cosmology have very precise models that describe the evolution of the universe at the largest scales. As we've seen, we have models of various quality in terms of modeling epidemics and how they spread around the world. There are models of how neurons fire in terms of computational neuroscience, models of how proteins and fold and molecules interact, models for how airplanes fly, etc. And these simulators, if you think of them in the language of statistics, they are causal generative models of the data generating process, meaning you can generate synthetic data from them, and the way that the data are generated tells a story about like some mechanistic model of how we actually think the data, how the thing actually works. And when you pair this with the expressiveness of programming languages and the power of modern computing, you have the ability to produce tremendous amounts of very high fidelity synthetic data. And so these are predictions, right? These are predictions from the model about what the data should look like in sort of statistical terms. The problem with simulators is that they're very poorly suited for statistical inference. I'm not going to go into the details, but they're very cumbersome to work with. And typically, for the experts out there, it's because they involve they're enormous latent variable models, and you have to integrate over a bunch of stuff, and those integrals are intractable. So that's kind of setting is actually very, very common in the sciences. And so this is a workshop, a excerpt from a workshop that was actually connected to the kind of machine learning community. I was trying to bring these two fields together. And they talk about a class of computational statistical methods under these intractable likelihoods that simulators bring. They say that these methods have been mostly developed beyond the radar of the machine learning community, but they are an important tool for a large and diverse segment of the scientific community, in particular systems and population biology, computational neuroscience, computer vision, healthcare, and many others. So what I really like about this framing of the problem is that it abstracts in a very nice way that's very portable across different domains. And there's a very natural way in which domain experts can inject their knowledge, and methodological experts can be kind of shielded from some of the details and still be able to contribute in a very meaningful way on a methodological. So somehow the interface here is just very, very conducive to use-inspired research. And I think that I'm very excited about this and where it's going and its potential to really kind of revolutionize many areas of science. So this is the topic that I actually gave the talk on at the NeurIPS workshop in 2016 in front of that sea of people. And shortly after that, there have been several workshops, but immediately after that, there was a workshop. And here you see basically a lot of the really hot topics in AI and machine learning at the time, these generative networks called GANs, various things coming together with kind of particle physics as examples, the idea that simulators are well suited for describing real world phenomena, and the connection with statistics. And so I'm just very excited about this convergence of these different ideas and these different sort of types of expertise on this topic. And we wrote some review paper talking about how machine learning and various other things are kind of pushing the frontier of what we called simulation-based inference. Okay, now, so that's what I have to say about that. I'm going to now step back a little bit and think about the scientific method more broadly, and really think about the scientific method as an ongoing process. It's not a one and done kind of thing where it's just you have a model and you assess its predictive accuracy. It's very open-ended. So the kinds of techniques that I talked about, which I'm very excited about, are still kind of isolated to this part of this diagram where we gather data and we're testing predictions. That kind of specific type of statistical inference and hypothesis testing, stuff like that, it's kind of sitting here. But if we think more broadly about like developing theories, hypothesis generation, designing experiments, thinking about interesting questions, trying to think about where, what experiment should we build next. All of these kinds of things are currently beyond what our best AI systems can do. And if you look at we have things like, why does this pattern occur? And, what are the causes of this phenomena? And these kinds of ideas are really things that start to fit into what's called, causality or causal inference. And they start to go beyond the kinds of things that we see in like normal statistical type of thinking, where you're just thinking about correlations between things. So if we go back to this paper by Bremen, he's like saying very insistently that the criteria for the models here is predictive accuracy. And I just like to contrast that with, what my feeling was at the time, things that I've been saying in the meantime, and also in particular a paper that came out recently on Monday, as a matter of fact, which I thought was interesting. It talks about on scientific understanding with artificial intelligence. And it says, imagine that we had some oracle that could correctly predict the outcome of every particle physics experiment. So they already had me there because they used particle physics as an example. So if you could do that, that would, it says, that would obviously revolutionize science and technology as we know them. However, as scientists, we would not be satisfied with the oracle itself. We would want more. We would want to comprehend how the oracle conceived of these predictions. And this feat, denoted as scientific understanding, has frequently been recognized as the essential aim of science. And now, and so I basically agree with this point, and this is like why we, interpretability and these kinds of things are important, at least in the context of science. But it's also interesting to think about how can AI be brought into that system. You don't need to throw away AI. The question is, how do you bring AI into that setting? And that's what they're also saying. How can AI systems contribute to scientific understanding or achieve this autonomously? And I think it's a really fascinating area and something that I'm interested in exploring. So here's a figure that they have from that paper. And one of the things that's nice is they actually talk about kind of a few different mechanisms for how that works. One of them is essentially, they call it a computational microscope, which is ways that AI essentially can, accelerate the types of computational experiments that, if you had infinite computing power, you would just do them, but we don't. But when you think about things like AlphaFold that have solved some of these, protein folding predictions, some work that's going on in, say, for instance, theoretical nuclear science, where basically if you had infinite computing power, you know what you would want to do, but we don't. And AI techniques are basically accelerating that dramatically right now, but without like fundamentally changing the nature of the question. And then there's the idea here, I like this, which is a resource of inspiration. And many people have talked about AlphaFold, if you're familiar with it. Yes, it has direct applications in terms of trying to guess the structure of some protein or something, but many of the people in that area are actually sort of most excited about it from thinking about a muse, an artificial muse that can be, a source of inspiration. And that's also been seen in the context of mathematics recently with theorem proving and things like that. So there's, basically a refined and more nuanced picture about how AI and science interact that's being developed right now. The other point I'd say is that even in the context of kind of traditional machine learning in areas like it was used before, even more industrial settings where you're not trying to understand the mechanism like in science, there's been, a recognition that AI and machine learning, particularly the kind of supervised learning approaches, are very data hungry. And if you look at like reinforcement learning techniques that play, millions or thousands of hours of some video game before they master it, it just doesn't look like how, say, humans learn. And so there's been some pushback on that. And there's been increased appreciation in the value of some sort of structure, assumptions of some form or another, which might be some sort of domain knowledge, or in the jargon of machine learning, this is often referred to as inductive bias, where you try to basically add some structure to the model so you don't need so much data to be able to train the thing. And so what's interesting is in the context of science, you have often have a very clear picture of what the data generating process looks like. And that kind of informs some idea of what the architecture of your neural network should look like. And so this is where we've seen things like graph neural networks and et cetera really take off. And what's cool about those is that, they're neural networks, but you can point to them and be like, that thing is a planet or that's an atom. And you can understand the messages being passed as forces and things like that. And so they admit a more interpretable type of scaffolding to be able to work with. And this is a very exciting direction as well, I think. And a lot of this has been driven partially by physicists, but one of the people that's been very active in this is Peter Battaglia. We've collaborated a little bit, and his background is actually human. He's a cognitive scientist by training, works with Josh Tenenbaum and company, and they have a strong, research effort, which is about physical reasoning and trying to think about how do we go from just sort of curve fitting to reasoning, and the point there is that, you talk about intelligence is about model building and combinatorial generalization via abstraction and sort of the infinite use of finite means. So you start to see themes like symmetry and compositionality and these kinds of things coming across. And Yoshua Bengio, who won the Turing Award for his work in deep learning, is even saying very similar things. So here's a slide where he's saying, what if we had the right causal structure? And he talks about if we did, then maybe we wouldn't need so much data to train these things. Maybe they would be more robust, especially to something that's called distribution change, et cetera. And then you see various people, kind of luminaries, debating about this and generally agreeing with the point. So what my message here really is that even the very, the leading figures in deep learning also recognize these kinds of themes. They're not just thinking predictive accuracy. They are more and more appreciating the role of domain knowledge and causal structure and things like that. So I'll be kind of quick, but since I mentioned causality several times, I just want to try to get across one concrete thing about causation versus correlation. I know everyone's probably familiar with the adage that the correlation is not causation. Yuta Pearl wrote a very fantastic book called The Book of Why. This is me with him at UCLA. And an excerpt from that book. And one of the things that, is I think just everyone should know basically is that that there's a hierarchy of types of questions that you can ask and what you can expect to answer based on data. And so the lowest rung of this data are kinds of questions that you can answer just with data alone. And so he calls these types of questions association. So this is where you're talking about correlations between two quantities. And so they're kind of, what if I see this? What can I say about that? But really just in the sense of correlations. So with all the data in the world, you are not going to be able to answer questions at the higher levels of this, what he refers to as the causal ladder. So a different class of questions are questions of intervention. Like, what would happen if I did the following? So like, if I take an aspirin, will my headache be cured? You're going to make an intervention. You're going to take some action and you're asking what would happen if I do that? And it's very subtle, but it's a different type of question than just correlations. And then there's another kind of, well, here's another question, like, what if we ban cigarettes, right? Like, what would happen? And these are obviously important for policymaking. And then there's an even higher level of questions, which are based on what are called counterfactuals, where you're saying, what would happen if I had, what would have happened if I had done the following? And so, was it the aspirin that stopped my headache, or was it something else? Would Kennedy still be alive if Oswald had not killed him? What if I had not smoked for the past 2 years? Would I still have gotten cancer? These kinds of questions, and these are very important also in like a legal context, et cetera. So, and these kinds of questions are again, you cannot answer with data alone. They really require bringing in different assumptions, and you might not want to make those assumptions. But if you don't come with those assumptions, you're essentially not going to be able to address these types of questions. So here's a quick example. I don't want to belabor this too much, but here are 3 very short computer programs that draw some random numbers, and then they generate X and Y, and then it makes a scatter plot of X and Y. And these little graphs are sort of stories about how the data come to be. In this case, X causes Y. First, you generate X, and then you set the value of Y. And the other one, Y causes X. And here there's a common, what's called confounder, or some unobserved variable Z, which happens first and affects both X and Y and leads to a correlation between them. And so in this example is constructed so that the correlation between these is exactly the same. So from the point of view of data, these three are indistinguishable. But if I were to go make an intervention, and if I were, for instance, to set the value of X to 3, that would be like I took 3 aspirin or something like that, then I can ask, what about the distribution of Y? And the interesting thing here is that the way that the distribution of Y responds to the intervention on X is different in these cases. And so that's what kind of shows you that interventions is not, it's richer than what you get from simply talking about correlations and just a bunch of data. And simulators, they capture these kinds of things and various other types of models that scientists typically create, have this kind of additional rich structure. And that's really at the heart of the success of science, right? So it's important. Okay, so I will say that now kind of like, not concluding, but like summarizing that part of the talk, I think that causality is really super important, and it's kind of at the core of what's missing from Breeman's 2001 article on the two cultures. And so while predictive accuracy, may be really important, what we've seen, even in the context of machine learning in an industrial setting, is that oftentimes when you evaluate predictive accuracy, you're evaluating it on data, assuming that data is the same as the kind of data, the same distribution as when you deploy this thing in the real world. And often that's not true because, maybe the training data that you used was, like if it's images, maybe it was under really good lighting conditions, and then you're going to deploy it in a dark room or, on a helmet of a biker or something like that. And so this type of this kind of shift is often referred to as distributional shift. Also really important is that the data collection process itself and the way that you clean the data and do all the things that you do to it will change the distribution of the data, and that can bias your results. So if the data pre-processing is different from one context to another, that's also going to change things. And so it's really important that the data collection pipeline is actually included and thought of as like part of the data generating process, and it must be taken into account. And these kinds of considerations are relevant, not only for like social and the scientific context, but they're also very important in the industrial context as well. And that is definitely appreciated. I'm not the only person saying this, but now, okay, so that's a lot. I know. I want to now kind of just step away briefly from the kind of domain, like the methods and the way it interacts with the domains briefly, and talk about a few other aspects of data science, which are also really, really important. And I'll kind of go back to when academic data science was really taking off. So in this figure that I showed, if I de-emphasize the methods in the thematic areas and instead focus on the middle part here, there were a few different themes of what we were doing, which were really important. So one had to do with career paths, one had to do with education and training. Here at UW, we have the data science facilitators that are doing a great job on that. There's also the idea of software tools and support. So for instance, engineering support, reproducibility and open science, which is really kind of, a broad kind of change of attitude about how science is done. Space, like literally buildings and, working space, and culture. And then we had a group that was doing ethnography and trying to evaluate how well we were doing and just like, witnessing what was happening in our institutes. And the ethnographers were like super awesome to work with and very insightful. And I really was super happy that we had ethnography as part of the Moore Sloan effort. So here's a quote from Freeman Dyson. He's a famous physicist, passed away recently. He says that new directions in science are launched by new tools much more often than by new concepts. And the effect of a concept-driven revolution is to explain old things in new ways, while the effect of a tool-driven revolution is to discover new things that have yet to be explained. And I love this quote. And I just think it's great. I mean, he's a theoretical physicist of like the highest caliber, but for his appreciation of tools, really like warms my heart. And I think, for me, it's very important that we in data science in the universities also recognize the importance of these tools and contribute to them. So recently I've been in some discussions with NumFocus, which is a fiscal sponsor for a lot of the open source tools that are used in data science. And so here you may recognize several of them, things like Jupyter, NumPy, Matplotlib, R is in here. You have various different things, Julia, etc. And so these are the tools, scikit-learn, etc. These are the tools that are really pushing data science in a very practical sense. And it's really important that we in the universities are contributing to them. So that's one thing that I would like to see happen in the Data Science Institute, is to foster a culture of contributing to these open source projects. Another aspect about tools, and it goes to kind of the nature of data science, and that it has both a domain component and a methodological component, is that the way that we've typically trained domain scientists is to be very deep in a certain domain specialty, and then have a little bit, thin layer of broad knowledge that's not very deep, to kind of contextualize what it is that they're doing. And with data science, we're seeing researchers where we kind of want them to have a second leg, where they're also very strong in the computational and methodological component. And that's asking a lot of a particular person. And it's also not necessarily the most inclusive thing that we can do in terms of trying to organize our field. And so Alex Hesley described these as sort of pie-shaped researchers, while traditional ones were T-shaped. So the ethnographers studied this a little bit and said, well, it's not just pie and T-shaped. You have various different shaped people. Some look like gammas, some look like M's, etc. And that maybe a more realistic characterization of what's happening is to think about practicing data science at the community level. And here they identify various different ways in which people contribute to different either sort of spheres of influence, from individuals to laboratories to developers and etc. And I think this stuff is all very, very interesting. And here you see, for instance, tool developers, etc. And that speaks to, I think, also that now it's not just methodological depth. The methodological depth, we're starting to see stratification of different types of specialties. And so this is, I think, another nice figure that talks about the hierarchy of needs for data science. And really AI and deep learning and stuff is really, the cherry on the top. And that when you really think about deploying data science, especially, in industry or any kind of real system, a lot of the time is just collecting the data, moving it around, cleaning it before you get into any kind of analytics, et cetera. Here you start seeing A/B testing, which is another form of like causal inference. And so we're starting to see specializations where, for instance, the field of data engineering is starting to develop and be recognized more specifically. One thing that's missing from this are those concerns that I mentioned earlier on the social side. So I'd say even below this, we should be thinking about, before getting started with any of this, we should be thinking about data privacy and ethics and fairness and trust, compliance, reproducibility, all these kinds of themes, should really be at the very base of the pyramid, probably. So of the people that now you've got like so many different kinds of things that you need to take into account, you're definitely thinking about teams of people, and the university has these various sources of expertise. One place that I was, very happy to see and sort of surprised at first, and maybe surprise you, is just the role of the libraries. So at NYU, Vicki Rampin was was one of, well, I think she was the first research, data management, and reproducibility librarian ever. But also at Berkeley and Washington, there were the libraries played a really important role in terms of, a lot of these kinds of themes I'm talking about. They also were the home for a lot of the training, et cetera. And I'm very happy that the University of Wisconsin has, and the iSchool have a very strong statement here. And I'm really looking forward to working with that aspect of the university. Laura Noreen was one of the ethnographers at NYU. She kind of pivoted to thinking more about ethics and data privacy. She ended up leaving academia, to go work for a startup company called Obsidian Security that does cybersecurity. And she got promoted to the level of vice president of privacy and trust. And I think it's really interesting here to see that how, leading industry are really taking on these kinds of considerations, from the very beginning and taking them very seriously. Laura is also responsible for kind of creating and curating the academic data science community newsletter, and I recommend that you subscribe to that. It's got all sorts of great content in it. So I'm coming to the end here. So that effort of first getting data science going and the kind of activities and discussions that were happening in the early stages of data science led to creating this academic data science alliance, which Brian mentioned at the very beginning. And so that's me here. And so this is so that group has been really very collaboratively discussing across data science institutes across the country to try to really promote data science and figure out like what works and what doesn't and what are the challenges, and to try to really refine what is it the data science is and really realize the promise of what there is to offer there. And so I'm very happy that that UW has is one of the founding members. And so I just want to end a little bit with kind of the status of some of these themes I've discussed at the University of Wisconsin. So as I mentioned, and as Brian mentioned, UW is one of the founding members of the Academic Data Science Alliance. So that's fantastic. They put out a member book that has a brief detailing of all the different data science efforts across the country. The CDIS, if you go to their homepage, I'm very happy to see this emphasis on collaboration, but also you see how collaboration leads to innovation. That's very much this idea of the virtuous cycle and use-inspired research. So I'm very happy to see that. If you look at there's an NSF-funded effort called the Institution for the Foundations of Data Science at the University of Wisconsin. These are some quotes from their website, but they're talking about while data science is making enormous progress, that outcomes that are arising from some of these machine learning processes are not necessarily always robust. They can yield biased and unfair outcomes. There's concerns about data privacy. So all of these kinds of issues, I'm very happy to see are being, are recognized, embraced, and explored at the University of Wisconsin. You again here see this is the Data Science Bazaar that talks about the importance of data in communities. Again, emphasis on sharing and protecting data. So this is all going in the right direction. I'm very excited about that. Even when we look at the other CDIS Red Talks, we see a lot of emphasis about bias. You see people like Alex Hanna, who's I guess also a UW alum and connected as a senior research scientist at Google in various kinds of issues. Are these kinds of techniques raising economic disparity? Could technology save us from racism, et cetera? So these themes are all present, and I'm very happy about that. Another one that I would like to plug is the next CDIS Red Talk, which I recommend you see. Joao, I've gotten to know him a little bit. He's doing some super cool stuff using computer vision in the context of livestock and streamlining those kinds of processes. So it looks a little bit more like you see data science in industry, but like really deployed like, in the farm and with all of the reality and mud and et cetera you have to deal with. And I'm also particularly excited that University of Wisconsin, I think, is very well poised to try to lead in these what's being called climate smart agriculture, livestock, and forestry, where there's recognition that data science and artificial intelligence really have a big role to play in trying to address like one of the critical problems of our time. And with that, I will conclude. And roughly, I will say that while much has changed since the term data science was first coined, we've seen the rise of deep learning, dramatically improved tools, increased awareness of impact on society, and a more mature understanding of the role of domain knowledge and causality and things like this. Much is also still the same. There is still a huge data deluge and an enormous opportunity for both science and industry. There is still a huge demand and shortage of expertise, and I'm really thrilled to be coming to the University of Wisconsin to lead the Data Science Institute. So thank you very much.
Hey, clap, clap, clap. What I can say is, wow, that was an amazing talk. And I've been chatting with Kyle for quite some time, but I haven't heard him speak at length in this way. Now it is 5 o'clock and people may need to leave. And so invite people to leave if they need to, but there also were a number of questions that came up. And I don't know exactly from the organizers, but maybe we could take 10 or 15 minutes if you have the time, Kyle, with some questions. So what do you think?
I have the time. I am sorry for going so long. I had a lot to say. So
Yeah. Okay. So let me just Deval, you still have your hand up. Are you there? Do you want to sort of synthesize from the talk? You had a question early on, but maybe your questions even changed at this point.
That's true. Thank you very much for this wonderful talk. What a fantastic presentation. Welcome. So the question I had was with respect to, I think some of it you already answered, like how does AI relate to data science? Maybe you refer to some AI systems, right? If you can just elaborate a little on what type of AI systems you were referring to. And then what are your thoughts of all this with respect to singularity? And then what is your vision in the space for next 5, 10, 20 years?
Yeah, well, I mean, in terms of AI systems, I was really trying to keep it broad. So, I mean, it really kind of runs the gamut from, the types of AI systems you see, for making recommendations and recommendation systems and things like that in industry. There's obviously we see AI driving machine translation and like, the voice recognition on your phone, all the kind of dictation. We're seeing, huge advances in natural language processing and things where you can actually just sort of give instructions and it will write code for you, things that look like science fiction, in a lot of ways. And then there are the things that are applied in terms of, the scientific setting. It's really, I kind of referring to basically everything, and there's not enough time to give them all suit. I believe you mentioned the singularity is this kind of idea that that if you actually started to get AI systems that really achieved some kind of level of general purpose AI, that maybe they start generating even better AI, and you have some kind of runaway effect, and that we should be thoughtful and prepared for some kind of doomsday like scenario. Where maybe AI, kind of Terminator style AI systems take over the world, or there are various versions of what to be worried about. And while I'm in some sense, I think it's very futuristic, and if you look at the state of the art AI systems and how they fail, maybe you shouldn't worry too much. At the same time, I don't dismiss that we should be thinking about that kind of stuff. It's a valid line of inquiry, and so it should be taken seriously. I'm personally not as worried about that as many other real world problems that are actually here right now. And then I don't remember the last part. Oh, where is it going in the next 10 to 15 years? I mean,
right.
Yeah, I think, well, it's changing very fast. I definitely am very excited about the simulation-based inference. I think from the point of view of, if you look at science broadly and you step back and you think about the role of statistics and like, in science, it's a very important aspect of doing science. For the most part, the statistical techniques were at first limited to things you could do with a pencil and paper. Then we got to a point where you could have more complicated sort of, likelihoods models and things like that. And then you could optimize them with numerical approaches, but you still knew what the likelihood of the data was. Then we got to Bayesian inference, where you wanted to be able to do integrals, but they were intractable. And we came up with Markov Monte Carlo and Markov chain Monte Carlo and things that allow us to solve those kinds of integrals. But again, the likelihood was still tractable. And now we're at the next stage of that evolution in my mind, where the likelihood function itself is intractable. And but you can still make predictions. You still have a generative model for the data. So essentially, in principle, it's there, but it's not in a form that you can use easily. And I think that if you look at so many areas of science have very well developed simulations, and there's just a huge disconnect right now between the state of the art of simulations and the statistical techniques that can leverage them. And what I think is happening right now is that the advances in AI are allowing us to kind of close that gap, and they're going to allow us to return to kind of grounded classical statistical inference with just ridiculously expressive causal generative models that are informed by domain expertise.
So
Thank you.
there's several questions that have come up in the sense of diversity. There's a diversity of areas of context, as you say, of data science. And is there sort of a core training, or is it a matter of learn by doing as sort of an apprentice model in specific areas? So there's this tension between what's core and how much do you need to specialize?
Yeah, that's a great question. I do think there is some core, and it depends if you actually want to start to practice some of these techniques, then some basic mathematical skills that you would need if you wanted to do, say, some statistics and some calculus ideas and things that start to be important. Not everyone is going to be doing that kind of thing, and so they maybe just need to be familiarized with like what are core concepts. And so there's a lot of emphasis, for instance, on data literacy at the University of Berkeley, California, Berkeley. Excuse me. There is a required course for all freshmen, which is called Data 8, and it's like an introduction to sort of data literacy, and that's for everybody. So and so I think, and NYU started doing something similar for undergraduates, and that is framed in such a way that it's meant to be broadly accessible, and in my mind, I think that there are some ideas that are core that should really be, we need to think about how to communicate these ideas to society broadly, so that society is kind of equipped to think about, how data is influencing their lives. And so, certainly there are some things related to, data privacy and stuff like that. There's also, I think actually these ideas about causal inference, some of those core ideas, the fact that there are certain kinds of questions you cannot answer just from data alone is a pretty important core thing. And it's related to a lot of logical fallacies and mistakes that happen. And also leads to a lot of unreasonable expectations of what you're going to be able to do with data. And that kind of increases this tendency that you're going to throw some like machine learning model at some data, and it's going to like start telling you, if based on some video, if this person you should hire them or not because they look like other employees that you've hired, those kinds of mistakes we should try to avoid.
Well, I think that it's a great comments to pivot to the last question coming from Larry Winkler. Larry, please.
Hi, my question is, I don't know how the university sees this data science. Do you see getting a bachelor's degree in data science, a master's degree, a PhD, and what would constitute an expert in the field of data sciences?
Yeah, that's a fantastic question. Different universities have approached that from different directions, and I can say a little bit about it. So that first, I'll just start with at New York University. It was one of the first kind of master's programs in data science. It also had a little bit more of a kind of academic bent to it, and compared to, for instance, Columbia, that had a more like trying to train people from like industrial data science type jobs. And then NYU, I think, launched the first PhD program in data science. And so I have a graduate student who's getting her PhD in data science. And that is definitely the way that PhD program in data science is definitely aimed more towards the methodological side of things, but it's usually still contextualized in some research domain. And you see people applying it from, cognitive science, music, neuroscience, to the pure, mathematics and statistics side of things. So that's, that's happening. NYU was late to start with an undergraduate program. In contrast, Berkeley kind of came out of the gate with a robust undergraduate program. And they actually restructured the entire university. Like they moved engineering, they created a new division of the university. So different universities have approached this very differently. Many universities basically just kind of stuck data science to the end of their statistics and computer science programs that they already had, or their different departments. And that would not really be so much in the spirit of what we were doing, for instance, in the Moore Sloan effort. At the University of Wisconsin, there's the academic programs are being distributed, are being, provided, one through CDIS, but also different departments are providing different kinds of specialties and different kinds of, data science degrees or, minors and et cetera. And so there's a much more diverse set of data science options at the University of Wisconsin and many universities that I'm familiar with. And also notably, the Data Science Institute is not, the charge of the Data Science Institute is really more about research and not on the educational side. While, for instance, at NYU, the Center for Data Science both has research and education as in its purview. So so different universities approach it very, very differently. There's a lot of, I think it will take some years to see how it shakes out and which model is better or not. I think there are advantages to the University of Wisconsin embedding data science specialties in different domains while also having a very clear, strong expert, methodological core offering. And so I think it's really interesting, and it looks, it's more complicated, but I think it's kind of healthy in the end.
I want to thank Kyle again, and I've kept the questions, and I'll pass those on to Kyle. So one more round of claps for Kyle, and we're going to welcome you coming to campus in July and bringing your perspective on the programs, on research, and on science and academia in general, and industry and society, the whole kit
and caboodle.
Yeah. Okay. And thank you all for coming here and for the very good questions. Sorry we weren't able to get every question along the way. So
great. Thank you very much.
Yeah. And maybe if you want to put on that last slide again about upcoming talks. So Joao Dorea is giving the next talk, which is going to be on April 21st. And then there's also, whoops, we just had it for a moment.
Share that.
April 21st, and I'm not sure if that's going to be virtual or in person, and then there will be other talks after that. But well, there's a talk on Thursday, the 14th as well. All right, thank you very much, and have a good evening.